this short video, I will be showing you how to use AOI Logic and or an inverter. These are the three basic gates that we will be using. So let's draw up a circuit. In most circuits, we will have an input and an output. The input is either going to be represented by off or on, but for Boolean algebra, it's not off or on. The off is 0, and the on, 1. We also have an output. In this case, it's a light. So when I take the switch and I flip it to 1, the light turns on, because I'm giving a logical 1, which means yes, or power. When I take the switch and I flip it back to a 0, it will mean off. 0 is off. So, what does this all have to do with and, ors, and inverters? This is an OR gate. It has 2 inputs and 1 output. In an OR gate, if one of the inputs is a 1, then it will output a 1. If neither are a 1, so both are 0, it will output a 0. This is the truth table for it. As you can see, we have 3 columns. The x and the y are the input column, and the z is the output. When both the x and the y are 0, the output is 0. When just the y is 1, then the output is 1. If just the x is 1, then the output is 1. If both x and y are 1s, then the output is 1. Let me label the outputs for you. There you go. This is the labeled OR gate. Next, let's do an AND gate. What an AND gate says is only when one input is 1 and the other input is 1, then I'll output. So when both x and y are 0, the output is 0. And only when x and y are 1 will it output a 1. The last logic gate is the inverter. This is a very simple gate. It will take whatever the input is and switch it to the opposite. This is Farmer John, and he has a problem. He has a stupid son. Now, let me elaborate. Farmer John has 2 light switches in his room, and 1 light switch in the kitchen, which is where his fat son spends most of his time. All these switches are connected to a light out by his barn. Now, he's very energy conscious, and he likes to flip switches. So when he had 2 switches where both were hooked up to the light, his son would flick it and waste a lot of power. What he wants is switches X, Y, and Z. Now, whenever switch X is on, then Y or Z will turn on the light. Whenever switch X is off, then no matter how many times you flip Y or Z, the light won't turn on. So basically, he wants X and Y or Z. So let's draw up a circuit for that. There you go. This is the logical circuit for it. When Y or Z is on, it'll go through the OR gate, and it'll produce an output of 1. But no matter how many times this is 1, it needs X to be a 1 in order to give an output. Let's see it in action. If I flip switch Z on, nothing happens to the light. And if I flip switch Y on, still, nothing happens to the light. So let me flick both of these off. Now, we're going to flip switch X on. Notice how even though we did that, the light still doesn't turn on. Now, when we flip either Y or Z on, the light will turn on. This is true for when Z is on, or when Y is on, or when they're both on. Now let's draw a truth table for this. This is the truth table for Farmer John's circuit. It might look like it's set up weird with 0s and 1s all over the place, but there's a method to this. The truth table counts from 0 to 7 in binary. You guys should learn how to count in binary. Anyway, there are 0s until Z is on and either X or Y is on. And this is true for the whole truth table. So let's put this all into a Boolean equation. When we wrote up the logic table, there were only 3 solutions when the output was powered. That was when X was powered, Y was not powered, and Z was powered. Or when X was not powered, Y was powered, and Z was powered. Or when X, Y, and Z were powered. These 3 clump of numbers means X, Y, and Z. So it's like an AND gate, and this plus sign is an OR. The little line above these letters is a not, so X, not Y, and Z. And that's all we have time for. In the next episode, I will teach you how to simplify Farmer John's circuit.